Hey guys, we are continuing solving problems from Halliday Resnick Walker, 8th edition, chapter 21, and electric charge is the name of the chapter. We'll be solving question number 8 in this problem. Problem 8 from edition 8. I'll read out the question. Four particles lie on the corners of a square. The charges are Q1 equal to Q4 equal to capital Q, Q2 equal to Q3 equal to small q. What is Q by Q if the net electrostatic force on particle 1 and 4 is 0? Is there any value of small q that makes the net electrostatic force on each of the four particles 0? Explain. So we are given here that Q1 is equal to Q4 is equal to capital Q, and Q2 is equal to Q3 is equal to small q. The four particles are on the corners of a square. So this is a square here of side A, four corners of the square. Now this one is capital Q, this one capital Q, this one is small q, and this one is small q. In the first part, we said we have to find out capital Q divided by small q if net force on particle 1 and particle 4 are 0. Force on particle 1 and force on particle 4 are 0. Net force on 1 and net force on 4 are 0. They are identical particles, Q and Q. Okay, so we'll consider one of them. The first thing we'll discuss here is what about the signs of Q and capital Q? Are they like charges or unlike charges? Okay. Again, so we'll consider forces on particle 4. This is the diagonal. This angle will be 45 degrees. Because this is a square, diagonal will divide the angle into two equal parts. And force due to particle 1 on particle 4 will be along the diagonal. Along the diagonal, repulsive force. Okay, along the diagonal, repulsive force. So that means this angle is also 45 degrees. Okay? 45 degrees because it is along the normal, along the diagonal. So this is force on 4 due to 1. Force on 4 due to 1. Now, if small q is like capital Q, okay, if small q is like capital Q, then force due to 3 on 4 will be repulsive force, and that will be in this direction. F43, force on 4 due to 3. And force on 4 due to 2 will be in this direction. F4 from 2, force on 4 from 2. Now these two forces must be equal in magnitude. Because charge is same, Q and Q, distance is same, A and A, both charges and distances are same, so force magnitudes must be same. If force magnitudes are same, this is F43 and this one is F42, then the resultant force is here. This parallelogram becomes a square because the two sides are same. So this angle is also 45 degrees. Meaning the resultant of these two forces is along this line. I'll call this F4 from 2 and 3. Force on 4 from 2 and 3. Okay, so the two forces are now in the same direction, so they'll add up. They'll not cancel out. So net force cannot be 0. Okay, cannot be. So if small q is like capital Q, then net force cannot be 0 because the forces add up. They are additive in nature. But if small q is unlike capital Q, what will happen in that case? Okay, so let me erase this stuff first. This one here. This one here. Oh no. Okay, so again the force from 1 on 4 is repulsive force and will be along the diagonal. I'll just call it force from 1. double superscripts, let's avoid that. Let's use single superscripts. F1, force from 1. Okay, force from 1. Now, force from 3 and 4, they must be attractive now because we're considering Q is unlike capital Q. So, force from that one is attractive. So, force F3, I'll call this F3, force from 3. And this one here, I'll call F2, force from 2. Again, the two forces are equal in magnitude because Q and Q are same, distance A and distance A are same. The two must be equal. If the two are equal, then the net force must be along the diagonal. So net force is somewhere here along the diagonal. I'll call this F23, the resultant of these two forces. Now you can clearly see F1 and F23 are in opposite directions. So they can cancel out. If the magnitudes are same, net force will be 0. So the first condition for net force to be 0 on particle 4 must be that Q and Q are unlike. So small q and capital Q are unlike charges. Okay, they are unlike charges. So one of them is positive, the other one is negative. Then only net force can be 0. Okay, and magnitude wise F23 must be same as F1. Then only they will cancel out and net force will be 0. So for a while now we'll only consider the magnitudes of the forces. That means we'll only consider the magnitudes of Q and Q. The signs will introduce at the end. Remember, if one of them is positive, the other one is negative, then the ratio must be negative. So we'll have a minus sign at the end. Okay. For now, we'll just use the magnitudes and introduce the minus sign at the end. So now, let's see. We'll first find out F2 and F3. Write down here. F2 is same as F3. Let's call both of them F is equal to gamma QQ divided by A square. Q1, we have Q for that. Q2, we have capital Q for that. And the distance is A between them. So the resultant of the two, F23, is equal to under root of F2 square plus F3 square. They are perpendicular to each other. They are perpendicular to each other. So simply root of F2 square plus F4 square. This is under root of twice F square. I'm writing F instead of both of them. So F square plus F square is twice F square. So this implies F23 is equal to root 2F. Instead of F, I'll write gamma QQ divided by A square. Let's call this equation 1. This is our F23. Okay. This is this force, F23. Now let's find out F1. Okay, let's find out F1. Now for F1, we need this distance, diagonal. Diagonal of the square is simply root 2A. Okay, root 2A. Let me use another color there. Red one. Root 2A. You can find it using Pythagorean theorem for this right angle. This is A, so this is going to be under root 2A. So F1 will be, now F1 is gamma Q into Q divided by root 2A whole square. Both charges are Q and distance is the diagonal length, which is root 2A. So F1 is equal to gamma, equation 2. Now remember, for net force to be 0, these two must be of the same magnitude. So F1 must be same as F23 magnitude wise. Now F1 is equal to F23. F1 is gamma Q squared divided by, what is it, 2A squared. And F23 is root 2 times gamma QQ divided by A squared. Let's check it out. Yeah, root 2 gamma QQ divided by A squared. Okay, so gamma and gamma goes, A square and A square goes, one of the capital Q goes. So this implies capital Q. We'll take the small q downstairs, divided by small q is equal to this 2 upstairs, 2 root 2. 2 root 2. Including signs. Now we have not included signs yet. We're not including sign. And we already know the two charges are unlike. So one of them is positive, the other one is negative. So the ratio has to be negative. Ratio has to be negative. So with signs, Q by Q is equal to minus 2 root 2. Okay, is equal to minus 2 root 2. This is our condition for net force to be 0 on particle 4 and particle 1. Particle 4 and particle 1. We'll get the same thing if we deal with particle 1. So, what is the condition for net force to be 0 on particle 4 is that this ratio Q by Q must be equal to minus 2 root 2. Okay, this ratio must be equal to minus 2 root 2. Now, we are being told in part B of the question that is there any value for Q? Is there any possible value for small q? For net force to be 0 on all the 4 particles. Now we know what is the condition for net force to be 0 on 1 and 4. The condition is Q by Q must be equal to minus 2 root 2. Exactly the same way we'll find out the condition for net force to be 0 on small q. Okay, net force to be 0 on small q. And then compare the two and we'll conclude if it's... Okay, so we just found for net force on particle 1, equal to net force on particle 4 is equal to 0 if Q by Q is equal to minus 2 root 2. Okay, if Q by Q is equal to minus 2 root 2. So this is our condition for particle 4 and 1 to be in equilibrium. Now, we have to see if small q, is there any value for small q for which net force on all the 4 particles is 0. For particle 1, which is capital Q, this one is again capital Q, this one is small q, this one is also small q. So let's consider net force 0 on this small q and then find out the same condition. Then we'll compare the two conditions and see if it is possible for all the 4 particles to have net force 0 or not. Again, this is a square diagonal. Force due to particle 3 on 2 will be this way along the diagonal, exactly the same way what we did earlier. Capital Q is unlike small q, that we have already concluded. So net force on 1 due to 1 is in this direction, F1. And net force from 4 is in this direction, F4. Force on 2 due to 1, force on 2. Magnitude wise, the two are same. Again, capital Q is same. Distance A is same. So force magnitudes must be same. So the resultant of these two forces must be along the diagonal. Okay, must be along the diagonal. This makes a square. So resultant of the two must be along the diagonal. I'll call this F14. Clearly, as we can see, F3 and F14 are in opposite directions. So if the magnitudes are same, they will cancel out. Okay, simple. Exactly same thing what we have done in the earlier case. So let's find out F1 and F4. So F1 F is equal to F1 is equal to F4 is equal to gamma capital Q small q divided by a squared, distance a squared. So resultant of these two, F14 is going to be under root of F1 square plus F4 square, exactly the same what we did earlier. So root of F square, this is F1 is F, F4 is F, F plus F square is twice F square. So this is root 2 F, F is gamma Q divided by a squared. So this is our F14. Let's call this equation 1 for this case. Then let's find out F3. Again, the diagonal length is the distance between the two charges, which is under root 2a. Okay, under root 2a. So F3 is gamma small q divided by root 2a squared. Which is gamma q squared divided by 2a squared. Call this equation 2. Now these two forces, this one and this one, magnitude wise must be same. then only they will cancel out and net force will be 0. So let's equate the two. Now F3 is equal to F14, implies F3 is gamma q squared divided by 2a squared is equal to F14 is root 2 gamma q divided by a squared. So anything cancels out, gamma and gamma cancels out, q squared, one of the q's cancels out, a squared cancels out. So this implies small q to this side, root 2 to this side. This will become 1 by 2 root 2 is equal to capital Q divided by small q. So this implies capital Q divided by small q is 1 divided by 2 root 2. 2 root 2. Including the sign. Now remember, they are of opposite signs. We have not included signs yet. We have just dealt with the magnitudes. If we include the signs, we know one of them is positive, the other one is negative. So ratio must be negative. So with signs, capital Q divided by small q must be minus 1 divided by 2 root 2. Minus 1 divided by 2. What was our condition for capital Q to be in equilibrium? So what we have found here is we consider equilibrium of small q. The condition for that is the ratio q by q must be equal to minus 1 by 2 root 2. And the condition for the equilibrium of capital Q was q by q must be minus 2 root 2. So for net force equal to 0 on capital Q, the condition is capital Q divided by small q is equal to minus 2 root 2. And for net force to be 0 on small q, the condition is q by q must be equal to 1 divided by 2 root 2, minus 1 divided by 2 root 2. The conditions are not same. You can either come up with this condition or come up with this condition. If you come up with this condition, q by q is equal to minus 2 root 2, then capital Q is going to be in equilibrium. That means particle 1 and 4 are going to be in equilibrium. Or you can come up with this equation, with this condition, then small q will be in equilibrium. Both particles, capital Q and small q, cannot be simultaneously in equilibrium because the conditions are different. Okay, because the conditions are different. So there cannot be any value of q. There cannot be any value of q for which all the 4 particles have net force 0. Okay. At the most, we can have either capital Q, the 2 particles of charge capital Q, to be in equilibrium. Let's look at the diagram. So either this one and this one can be in equilibrium, or this one and this one can be in equilibrium. Net force on either this one and this one will be 0, or on this one and this one will be 0, because the conditions are different. Okay, conditions are different. Fine.